Okay, good morning. Let's go ahead and start. Sorry, as usual, I guess hopefully everybody knows we've got stuff a little bit before now, so yeah, it's usually going to be 8:20 or so before we get started, it looks like. Of course, we're down to the last 2 weeks, so reminders for people. Let's see here. If you have any questions, let me know, we're going to be finishing up the ensemble learning, although I would recommend people maybe get started with the last, looking ahead to, make certain that it's visible. The dimensionality reduction stuff, supervised learning, we might want to make certain that you can start looking at those. Um, Effectively, what we've got 2 more weeks face-to-face classes or online streams here, and then a finals week. And I brought this up before. Our schedule was a little bit abbreviated, unfortunately. So we still have the assignment 6 on ensemble learning due at the end of this week. And probably today I'm going to talk about that, but maybe on Thursday we'll get started on some of the unsupervised learning stuff. So, make sure we continue working on that. Yeah, that's right. So I have officially made that due at the end of this week. So you can still be working on the ensemble learning stuff, and we'll continue talking about that today here. But yeah, we're gonna have so we don't have too much more time. There is one more assignment, one more test, and one more and the class project. So I want to kind of remind everybody about all those. Because of the way timing worked out, I am just going to go ahead and make those all due basically during finals week. So I'll give you as much these last 3 weeks to do those final things after you finish up assignment 6. But we're at the end of the semester and stuff, so people probably should be aware of that. And I would certainly highly recommend that you might want to try and finish up the assignment at least, say, the week before. If not, also get your kind of class project mostly done. I will also open up the test and have it available for quite a bit of time, just because I know I've squeezed things a bit here, so I want to be flexible. So probably maybe starting the week before finals week, like Thursday or something, I'll probably go ahead and open up the second test as well, and give you like a full week, the last couple of days, or the weekend, or anytime during finals week to actually attempt the test and finish it up. So. But yeah, let me know if they have any needs or concerns on making due dates and stuff like that. So, I am trying to. I will pretty much accept anything of these last 3 assignments up till like the Thursday or Friday of finals week. Although I'm gonna be trying to evaluate stuff incrementally, just so I don't have everything to do over the weekend after classes are done. So yeah, also I'll remind people about the class projects. I still haven't looked a whole lot at those. I have seen some people are beginning to do some stuff on there. Making commits. Some people have been asking some questions and things. But yeah, don't forget about that. It might be a good idea to. That would certainly be one thing that you could mostly get done in the next week or two, so that you get that mostly out of the way, so you could finish up the other things I'm asking to do on this class here. A few more links here. I've been. Hopefully, most people are kind of in the meat of things on your kind of project. So you probably want to be thinking about certainly getting to the point where you're thinking about final things or wrapping stuff up, or at least beginning to plan for that. So a few more links for people that are interested. Some of these are stuff that we already covered, but there's always good advice on things like, I brought up most of these before that I mentioned in the announcement that I just made the other day. Um, Make certain that you are using the some mechanism and documented it so that I can kind of reproduce your work. So, make use of the environment .yml or some other mechanism like that to show dependencies and so that I know which things need to be installed and what environment needs to be set up. And I guess the only I had been debating, maybe talking a little bit about having some sort of a write-up, like more than just your IPython notebooks. It's not really a requirement, but hopefully people are doing enough work that it would make sense to have more than one notebook. So like a notebook maybe where you talk a little bit about your data exploration. Maybe you have another notebook where if you had some decisions on some cleaning and stuff of how you prepare your data for doing your primary modeling or analysis of stuff, and then maybe a notebook or two where you are exploring different, fitting some different models or trying to improve things. I did have somebody ask a question. I mean, this is only a semester-long project, so I'm not looking for people to do state-of-the-art or actually beat the best performance on their data set that you might have found or that people have been able to do on things, right? So I am looking more for people to demonstrate, using scikit-learn and using machine learning tools like we discussed in this class, applying the at the end, I am hoping people either do a regression or a classification or maybe both. It depends on your data set, but do some sort of modeling. I guess one thing I maybe should have mentioned on that, we are down the last 2 weeks. I often have a lot of people jump in and start doing some stuff with like some neural networks or deep learning, which is fine, but you really should. This class is a little bit before that. We don't really get into that topic. It's a good sort of introduction to the things you need to know before you start learning about neural networks and things. But yeah, for that, with that in mind, it would be a good idea, even if you do want to dabble in some neural networks or something, that you do demonstrate some more basic models. So, you can always use those as a baseline, but show, like if you're doing some sort of a classification task, show what performance you get with a logistic regression and k-nearest neighbors or something like that. So maybe compare a couple of some of the core machine learning algorithms. At least some of the things that we covered in this class. Logistic linear regression, support vector machines, decision trees, ensembles, maybe some unsupervised learning, although we haven't really talked about that in class yet, but that's kind of our last week here is going to talk about some unsupervised learning methods. All right, so I think that's all I'll say about that again. Maybe I'll try and give some more hints next week, but if anybody has any questions, let me know. So like I said, I've had one or two questions, people work on the class project. So I did begin saying also that I won't have like a formal, that you have to have like a final report or something, although, that's not necessarily a bad idea, but you should also, at a minimum, strive to, have at least some description in your notebooks, if not like a separate kind of final report document. So by that I mean, so think of the typical sort of written paper technical report. So you might want to keep in mind in your notebooks that you have things like introduction, something where you talk about your methods, something where you kind of show your analysis, and then maybe some conclusions, results, kind of thing like that. Often you can have that in sort of every separate notebook. You can kind of structure it at least in some basic things like that, and do use the textual part and write up and describe and document kind of your thoughts and your results and things like that. Okay. So yeah, for the rest of the time today, I was going to go back to ensemble learning. And there was one particular thing we kind of got into a lot of this stuff on Thursday, but yeah, let's look at kind of decision trees a little bit, but also talk about like the building ensembles by hand. So like stacking ensembles. So that's often on the assignment 6. If you haven't been working on it yet, often the last task where you have to build a stacking ensemble is the one that is the most that most people need a little bit of help with or some hints with. So yeah, I'm not going to talk any more about decision trees. So let's move on to basic ensembles here. So most of the assignment 6, if you haven't looked at it yet, is sort of using basic voting ensembles and using some of the built-in ways of doing that on Scikit-learn. There's kind of probably, if I had to pick one thing on sort of the ensembles here, I mean, definitely, try and spend a little bit of time understanding how random forests and extra random forests work. So I think I've mentioned it before in class. It's a relatively simple idea, but they actually have pretty good performance. So among, when you compare them to like support vector machines or some of the more things that will give better performance that we kind of cover in this class, random forests are still pretty good. They're often a good thing to check how they will work on your data set. You need especially like classification, model-produced classification. So, but both random forests or kind of just ensembles in general, you can kind of break them up into this basic idea that we're going to create a bunch of classifiers and then combine their results somehow, right? So the difference between kind of the voting classifiers and this bagging and pasting and then these forests is whether you're using all of the same kind of classifier, so using a bunch of decision trees, or if you're using an ensemble of different methods. A forest is really just an ensemble of a bunch of decision trees, but you have to. We'll talk about it here, but yeah, you have to do something to make certain they're not all basically identical. So it doesn't do you any good to ensemble a bunch of classifiers that are really just all making the same decision or really just the same classifier. So there has to be some difference, some randomization or other differences among the things that you're bringing together. So back to the basics. So I don't know if this, this again is kind of discussion directly from a textbook. Intuitively, what's happening here with ensemble is some people have sometimes heard of the idea of the wisdom of crowds. It's kind of related to some of those concepts. So often, the individual, no matter how good they are, can be outperformed by a bunch of not necessarily experts if you have a large enough number of them. So if you have a large ensemble of people voting on something or making predictions or bets about something, the individuals might not necessarily be experts or know a whole lot about the field, But because of the large variety of experience and knowledge that they have, if you can ensemble them together, like in a voting market, which is kind of in the news right now, or so a betting market, or just some sort of voting, you can often get better decisions as good or better than like a single expert by ensembling a bunch of weaker votes. Right? So I don't know if this example is exactly right on because it's directed from the textbook. So the idea here is that we have a bunch, we're just doing coin flips. We have a biased coin that's like always giving 51%. So 51% of the time it comes up heads, 49% of the time it comes up tails. So if you have an individual one that flips, 10,000 times, you can end up with something that's quite biased. But if I do 10 of those and take the combined or the average of the 10, you'll tend to get much closer to the true answer, which is that we're a little bit biased on this coin flip. So the blue line here, if it wasn't clear, if you read this, is really just the ensemble says it's really just the average of the other 10 that we had here, right? So after 5,000 or after 10,000 trials, some of these were kind of a bit high and some of them were a bit low. Presumably, the reason why I don't particularly think that this example is great is if since we have 10 of these, if I just had one of those, but you continued it on for 10 times longer, you should get a similar, usually get a similar result to having the ensemble of 10. So this is kind of like just doing 100,000 trials instead of having 10 separate trials of 10,000 coin flips here. But the analogy is kind of sound. So usually, whenever you do this, you think of these as sort of weak experts, the 10 trials that we had, and you're ensembling them together, you should pretty much always expect to get something much closer to the true answer here, which is we have a slightly biased coin. Then, so you can see that one or two of these were as close, if not closer, than our ensemble, but a lot of them were further away in this example. So anyway, the point of that then is, that so this kind of combination of weaker classifiers or weaker learners can, in some cases, give you a better result than just a single really good classifier. Okay? Not always the case, and in fact, so that's another thing for the assignment that you're working on. You might not get results that are much better than the individual. In fact, you'll usually, I think, you might get a little bit of an improvement from the ensemble over the best classifier when you do these for task 1 or task 2, but it won't be a whole lot of improvement. It may or may not be too significant. I can't remember. I think it's maybe usually slightly better, but it's debatable whether the improvement is significant or not. But I don't remember if the textbook goes into this. Ensembles of this first type, where we're like a voting ensemble that we're talking about right now, these are often like if you look at contests for doing machine learning contests like Kaggle or something like that, often people will start off by building kind of the best classifier they can for the state of the art. So build some random forests or some deep networks. But then in order to tweak out and get maybe another percentage or two better performance, at the end they might start combining using like an ensemble like this. So take a couple of their best approaches and build a voting ensemble, and that can often end up with another 0.5% or percentage or two better performance in terms of your classification performance or mean squared error if you're doing like a regression or something like that. So let's see. Let's look at this example. we're up to the point where I kind of left off on last week. So I did get into the basics of talking about a voting ensemble. So there are two. The basic idea, and it's good enough to use these ensembles or to do the assignment, is that we can do basically a hard vote, and most people can understand that pretty easily. So if you think of a binary classification task, so here we're using, I think, the Moon's database again, a made-up data set where we're doing a binary classification task here to show the result of an ensemble. So, if my answer is just for a binary, a 0 or 1 or true or false, and if I train 3 different classifiers, to start with, or on like your first pass for the assignment, we can use very different methods. So like train a logistic regressor and a support vector machine, and so we did a we did logistic regression, a basic decision tree, and a support vector classifier in this example. Again, it's probably the same example in the textbook that was given here on this making moons data. You can build these by hand. This is pretty similar to what you're supposed to be doing for the first task, I believe, first 2 tasks or so. So hard voting is really just a majority vote. So when you have so it's simple to understand how that works for binary classification. So if I have 3 classifiers, whichever class receives 2 or 3 of the predictions for the classifiers would be declared the winner if we're making predictions on new data. And by the way, so I didn't talk about this last time, but the API for this should be familiar. So once you build one of these voting classifiers, right? So here we're using the voting classifier from scikit-learn. We pass in basically, there's different ways to do this, but we'll pass in a list of tuples. So these will be the estimators or classifiers that we'll use. But then after that, you can treat this like any other estimator. Like we've used in scikit-learn. So this voting classifier will have fit in order to fit a set of data. What this is actually going to be doing is going to actually fit for each individual estimator data that you give it. So we'll train the 3 estimators by calling this. And then if you ask for a prediction, like we do here. So again, the voting classifier has all of the same methods as the estimators or classifiers that we've seen before. The basic ones being like fit and predict. So yeah, I don't remember. By calling fit before, we should have already fit these. So I don't know if it was really necessary to call fit again. Although that might I have to go back and think about what's happening here in this example from the textbook. So that might be training the classifiers again a second time on the same training data that we did here. Let's check. We can check that out. So for example. I don't think we really need to refit there. So we're showing that we're using the logistic regression classifier, the decision tree classifier, the support vector machine classifier, and the voting ensemble as a whole here. And we should have already fit those up here. And by calling the fit here, that should actually train also the individual ones. Right? So redo this here. Let's run everything above that. And guess what? So yeah, looking at that, I guess that even though we've got handles to these objects, I guess when you pass it into the voting classifier, it must make a copy of those because yeah, so yeah, we did that. You do have to call the fit on the individual ones here. Oh, the other thing I think on the assignment, maybe the last 5 or 10 minutes, I'll bring the assignment up directly and look at this. So I think on the assignment, I do ask you to do a similar thing to what we're doing here, but we ask you to actually access the fitted classifiers inside of the voting classifier. Right. So instead of doing this, we should be able to. There's a way to query one of these voting classifier instances to get access to the individual classifiers that we have. We show. So yeah, we might not have had an example of doing that in the textbook or in the assignment notebook that we have here. So if we were to look at, let's look at it real quickly. So if we were to look at our voting classifier that we have at this point, so yeah, this is kind of what I was thinking at. So I might be giving away a little bit, but this would be another way. So you can actually get access to the estimator. So estimators is just a generic name for the models that are part of the ensemble here. But I think estimators is used because we could have an ensemble of regressors as well. So there might be classifiers doing a classification task, or there might be regressors that we're ensembling. We don't talk a lot about an ensemble for regression, but you can do that as well. But I'll leave that. I think the textbook talks a little bit about ensembling some regressors together. Ensemble regression. Yes. So anyway, I think it's the which one is it? Estimators. So if you access the estimators, you get back your list, but these should be the actual ones, I believe, that were fit on the model that we just did in the cell above this. So for example, if I get the first one at index 0, that's a tuple, and I can get the actual regressor, which is an instance, and then we could do the same things like we're doing down here. So predictions. So it's the test data. Huh. It does not fit yet. Let's look at it. I'm a little bit surprised by it. I thought that was right. Oh, there it is. So yeah, there's a. I mean, I need to look at the documentation. So it's the estimators underscore. It must be the one that has the fitted model. So I don't know if people know this convention in scikit-learn and a lot of places in Python. Whenever you have an underscore after a member variable, that means that it's supposed to be like a private or internal to the class there, but scikit-learn does expose those at times, and sometimes you need to access those. So we can look at these. So, for example, bring up the help here real quick, since I'm showing this as an example. So just looking at the PyDoc documentation for the voting classifier, Yeah, the estimators with an underscore is the collection of the fitted sub-estimators. So that should probably that would be the thing you might want to use for your assignment. Although you can also use the name estimators. I forgot about that. Those names that are used on the tuple. Basically, the named estimators is just a dictionary. So another way you could get those instead of going through a list is I could say I want the particular one that we named LR, logistic regression. Okay, anyway, yeah, so I guess that's maybe something to keep aware of. So there's both like an estimators and named estimators with and without the underscore, and those are apparently different. I didn't realize that. So the one case, I guess the estimators without the underscore is the original parameter that's passed in the list of the classifiers that you want to train. But the one with the underscore is going to be how you access the one that should have the fitted estimators after you call the fit model on the ensemble. So anyway, yeah, I mean, that, just to wrap up or back to this. So however we do this, we are actually fitting the different classifiers, but they should end up with a pretty similar result to the classifiers that were fit inside of the voting ensemble. So, so this is what I was kind of talking about here. You might get something similar on the assignment that you're working on now. So for this made up Moons data set, we don't really get an improvement. In fact, the voting classifier, it's just look at the percentage correct is what we're showing here, the accuracy score. We're getting about the same as the best classifier, a little bit less. And there should be some randomness in there. So if we rerun this each time, we should get a little bit different results. So I think. So yeah, right. So since we're not setting a seed in this notebook, you'll notice that you can end up getting where the voting classifier does a little bit better. It's a good percentage point better that time. So there's some variability in the Moons data set is random, and the classifiers themselves might be slightly different each time we rerun without setting a seed. So yeah, I don't know if that's always true. So it might not always outperform the individual classifier. Should get close, but you might see something the same in the assignment 6 that you're working on. So it's not. I keep coming back to that. It's not that necessarily that you've done anything wrong if you're not getting an ensemble, a voting ensemble that does better in the assignment that you're working on. You're probably still doing it right. It should be close to, if not maybe a little bit better than the best individual classifier, but not necessarily a whole lot. Okay, and so I do ask you to also do some stuff with the soft voting. So the idea on this is that the way that most machine learning, like in scikit-learn in general, work. When you fit a classifier, you can often give some estimate of how confident I'm going to be on my predictions, right? So how that happens, how that works, is going to differ depending on the method that we're using, the estimator that we're using here. We've touched on those sometime previously, like when we talked about decision trees, for example. the way to estimate, so when we end up down in the leaf node, we're going to have that Gini index score. So we can use that as an estimate of how confident when we get to that point, because that is telling us, not the Gini score, but the actual breakdown of that we have for each of the classes. Right? So decision trees and many other classifiers directly support the predict probability, which is, I think of that as kind of the confidence. So how confident you are on how confident the estimator was on each of his decisions. Not all of these do. So I don't know. We might not discuss it in class, but if you read the textbook, support vector classifiers don't, because of the way that they work, don't directly support this, but you can actually indirectly, when you fit or when you create a support vector classifier, if you specify probability is true, it will do some extra work in order to also create a data structure for the support vector machine, so that it can also estimate its confidence or the probability. So in scikit-learn, most of the estimators that don't support this directly will usually have something like support vector classifier does here, that you can say, well, even though you don't support this natively, still make it possible so that I can get confidence or predictions on those. So doing soft loading using the confidence or the prediction probabilities can often give a slight improvement when you're doing these ensembles, which should make sense, because assuming that these predictions are relatively accurate, if I give more weight to the classifiers that say I'm pretty confident about this, and I give less weight to the estimators that are saying I really am not certain, it's a 50-50, I'm just guessing at this one, then hopefully the ensemble of their performance will improve, taking into account how certain or uncertain. So you can do that by using like a weighted vote or a weighted average, using this predict probability. I'm sure people have used that before. That method, we've come across it in previous assignments. So here, if we do the soft loading, again, well, yeah. So again, we're going to get some random stuff. So it actually didn't do as well as we did before, but it is working. So because of randomness, again, you won't always get really good example results here. But it won't so using soft loading won't necessarily guarantee that it will improve performance significantly, but sometimes it will. It should usually give as good, if not a little bit better, than doing hard loading most of the time. And just to show you what that predict, I can't remember if I've ever explicitly kind of shown this, but I'm sure that you guys have run across this before. So notice what's happening here is for every one of the data we asked to give the confidence on our data. This is a binary classification task. So for the first one in the test data set, it says that it's a 91% chance it's the class 1 and an 80% chance it's the class 0. So that's all this is doing. So it's giving, and if you have a multi-class classification, so when we looked at decision trees where we were using the iris data set, there would be 3. Basically a prediction for every one of the 3 classes if we have a multi-class, 3-class multi-class. But those should add up to 100%. So this should be a good probability distribution. That's the way the predict probability is supposed to work for all the classifiers in the scikit-learn interface. So you can see here that most of the time it's relatively confident on the one or the other. But if you look through all of these, you'll probably find some more examples that are closer to 50-50 or it's not so certain. So anything that's kind of at the boundary here are going to be less certain versus things that end up away from the boundary for. So this, we were using the logistic regression classifier when I just did it here. Try the same for the sport maker machine and so on. See here. I wanted to actually. I think let's go up to random forests. So real quickly, to kind of understand some of the subtleties of how random forests or extra random forests work, the extra trees. You should read through the discussion on bagging and pasting. So yeah, I mean, real quickly, so another way to build an ensemble is you could imagine building an ensemble of a bunch of all of the same type. Like I could have an ensemble support vector classifiers or logistic regression, something like that. But if you do that, you have to be careful that you're building estimators that differ somehow. So the common way to do that is to add some randomness in there. These are relatively easy to do for decision trees, which is why, so random forest is really just an ensemble of a bunch of decision trees. Extra trees are also just the same thing, an ensemble of a bunch of decision trees. We discussed this last Thursday, so you can easily add some randomness in there. So the typical approach is we're going to build decision trees, but so if I build an ensemble, a random forest of say 100 decision trees, for each one of the 100 trees, I might select a random sample of the features, only use a subset of the features. So that's really what bagging is. It's a fancy word for so yeah, bootstrap aggregation. So the bagging, the bootstrap aggregation. Okay, yeah. So both of these, I'm remembering the terminology here, the bagging and the pasting. They're both names for a type of sampling. So in either case, what we're doing is we're going to either sample the number of features, or another thing you can do is you can sample the actual examples, right? So if I'm doing 100 trees, I might, if I'm training with 1,000 examples, I might train each tree with only a subset of 100 of the 1,000 inputs that we have. So you can do it either way, or you could break it both ways. So you could take a random number of features and a random subset of the input data, right? So think of it as your training data as like a table. So all we're talking about sampling here is whether we're sampling some subset of features or some subset of the rows, which are the inputs, or you can do both. So bagging and pasting just refers to, and in my experience, I don't know, I mean, in some cases, these can make a big difference. But yeah, if you're doing sampling without replacement, so that means that I could potentially, if I'm doing bagging, and if I'm sampling the rows, which are the inputs, I could end up having the same input multiple times be sampled, which will enhance the variability. It'll just make that one that ended up selecting the input multiple times will be more likely to get that one right, or will have that as examples of this training. Where pasting is just doing sampling either of the features or of the inputs without replacement. So you'll be guaranteed, if you're using the pasting, not to have repetitions, multiple instances of an input or multiple instances of a feature when we're doing our sampling. Okay. Oh, and yeah, I forgot about this, but you can actually build one of these kinds of sampling classifiers by hand. So, but yeah, the whole point of this is really just showing a random forest is just really a bagging classifier. So these should be equivalent, if I remember right. So basically, a bagging classifier of decision trees, where you use the same parameters for the number of estimators and things, should give you pretty much exactly the same results. So a random forest is really just a collection of a bunch of decision trees. Like we're doing here, we're building it with 500 decision trees. We're using these meta parameters for all the decision trees, but since it's a bagging classifier, it's going to select. So it automatically uses soft voting, and it should select on the training data set. You train it, it should be sampling the inputs randomly for each of the 500 estimators that we have. If I remember right. So yeah, each trained on 100 training instances randomly. Okay, so this is, I think we'll go ahead and kind of wrap it up there. So that's the basics. I didn't quite get to talking about then this idea of stacking. So I just realized that we don't have actually a lot in the notebook on this idea of stacking things together. So the last task on the assignment 6, and I'll go into details on this on Thursday in case anybody needs some questions about this. So the basic idea behind stacking is, so for the ensembles that we've looked at so far, they make a very simple decision in order to combine together all the estimators. So some sort of either soft or hard voting. So with the idea with stacking is, what if we ensemble a bunch of estimators? So again, I think on the assignment 6, you're supposed to use the same ones that we were doing before. So you might use like a super vector classifier, logistic regression, maybe decision tree. I think you had like 5 you're supposed to use. Train these, but instead of doing like the voting, whether it's hard or soft, we take the outputs from these. So you can take either just the final decision, or you could take the confidence, the probability predictions from each of these, and train another classifier. We're using the outputs of these to train yet another classifier to make the final decision. Right? So instead of doing a simple vote, we're just building another model, which is using the output of the individual estimators on the ensemble to learn to make hopefully better predictions. So that's really the whole kind of secret of this. And once you get to that last task in the assignment, we kind of step you through building that up. So that you train some individuals by hand, but then also we need to split the data into train, test, and validation sets because we need to separately train these on some data, and then this classifier needs to be trained on something different than what we trained the individual classifiers for. when you stack these together. But yeah, so that's the basic idea. And again, in some instances, stacking things together can give a really big boost in performance, but it's not guaranteed. It's not going to be always the case. And in our assignment 6, you probably won't see too much, if any, improvement over the ensemble that you do before you create the stacked ensemble. Okay, so yeah, that's it. I'll go into more details of that next time. But let's go ahead and wrap it up from there. Let me know if you guys here have any questions. I didn't know any questions from people on the line, but all right. Okay.
Is it mandatory to prepare a separate document for?
It's not. Yeah, so I'm not going to.
We can include that in the notebook. Our explanations.
Yes, you can just write up. Just try and be clear. So I won't make a requirement for like a separate final report or document. Just do be careful to be explaining results and things in individual notebooks. I've played around. I've thought about that, but maybe in the future I might do that for some future classes. But so I haven't really put that in as a formal requirement right now.
I did the weekend, and on the first pass, we had to plot the two most correlated right? So when I turned it in, I did this. I'm trying to do it quickly because I could have a project this week. I want to get this done so I have to work on it. Yeah, I think I met with this because I did see the cool format because it just automatically cut it. But then really you can't really see it well, and this is kind of thickness. So I went back and did it. So let's it gets more clear.
Yeah, a little bit. Yeah.
Do I need to turn it in, or is that this?
No, the either one of those was fine. Yeah,
Okay,
it wasn't. That wouldn't be a big deal. Yep.
Yeah, for the project, I know it doesn't have to be big, but it's not like that limit because actually currently the data I have, because when I was reading it, and then I read it carefully now, because actually it's